Get started on this so we can finish this up. We're going to finish 9.1 today, and then I'm going to introduce some stuff for 9.2 and 9.3. So we're going to quickly review what we talked about yesterday. So we were talking about sequences and series, and we talked about how we want to write down what we call a general formula or an nth term formula. And the basic ground rules, how are we doing back there, Cameron? Okay. The basic ground rules are the formula should produce the first term when we plug in a 1, it should plug in the second term when we plug in a 2, and the third term when we plug in a 3, and so forth. So we talked about that exercise that we did on that other worksheet that we started last week, how you could come up with a ton of different formulas, but you want to make it so everybody understands that if I plug in a 1, I get the first term, and so forth, like we were talking about. We introduced what a factorial was, and we wrote down a bunch of, some of which were kind of funky sequences. And then we came up from formulas that were, or we came up with formulas for sequences that were written in expanded form, and we came up with an nth term formula. And we pointed out the idea of this index. It's like a counter. It's the subscript on the number of the term, and it's also the number that we plug into the formula. So if I put a 1 here, that means it's the first term. I put a 1 right there and a 1 right there. That's why I end up with a 1/2 here. We also talked about how you can do these using function notation. So this one we wrote down as C of n. So if I put in a 5 here, that means it's the fifth term. If I put a 5 here, a 5 there, a 5 there, this is a 5 on the top. 5 plus 1 is 6. 5 plus 2 is 7. That's why we have a 5 over 6 times 7. Everybody good there? Okay. We also talked about a recursive definition, and that's one where you use previous terms to make terms that come after it. Okay, so you've got to have a starting place. They've got to give you 1 or 2 terms to start with. It depends on what the recursive formula asks for. And then it tells you how to get from one term to the next. So the way we find this one is we take the previous one and we times it by 4 to get the next one. So take the previous one, times it by 4 to get the next one. This was the Fibonacci sequence. And on this one, you take the 2 previous ones, add those together to get to the next one. Okay? And then we talked about series, and series are where instead of having commas in between, we put addition in between and we add all the terms up, okay? And we talked about how we can have a finite number of terms or an infinite number of terms. And what's this letter right here? Sigma. Greek letter sigma. It's a capital letter S and it stands for sum. So let's take a look at this. So this is the definition of sigma notation. So when we say, this is how we'd say this. We'd say this is the sum from I equals 1 to n of a sub I. So what that means is plug in a 1 to get the first term, plug in a 2 to get the second term, plug in a 3 to get the fourth term, and so forth, all the way up until this number right here. That's going to be the last one. Okay? Again, this is an index. Okay? So that's the index of summation, and this is what we call the upper limit. This is where we stop, and this is the lower limit. This is what we start with. Okay? And then we always go up by 1. So start by plugging in a 1, then plug in a 2, and so forth. It's just the counting numbers. Okay? So for this next example, it says, write out each sum and determine whether it's infinite or finite. So let's just write out what this sum would be. If I plug in a 1, that's going to be the first term. So that's going to be a 1 squared over 2, so I get 1/2. Then I write a plus. Plug in a 2. That's going to be 4 over 2. And I'm going to write it that way. So I'm just going to write 4 over 2. Then I plug in a 3, that's going to be 9 over 2. Then I'm going to plug in a 4, that's going to be 16 over 2. And then I'm going to plug in a 5, that's a 25 over 2, and I stop right there. So because I stop, is this finite or infinite? Finite. Okay, any questions? Okay, need you to watch up here. Okay, do you recognize those numbers on the top? They're all the perfect squares, right? 1 squared, 2 squared, 3 squared, and so forth. Okay. The reason I wouldn't simplify this one and this one, even though 2 goes into 4 and 2 goes into 16, is because it's easy to recognize the pattern. And if I actually had to physically go through and add these up, it's nice that they already have the same common denominator already. Does that make sense? So be smart about the way you write that. Okay. Let's take a look at this one. So the first thing I do is I plug in a 1. If I plug in a 1, I get negative 4, and then I'll write a plus, plug in a 2, I get negative 1, plug in a 3, I get plus 2. Okay, what's happening every time with the terms? Negative 4, negative 1, 2. What's the next one? Next one would be 5. It's going up by 3 every time. Now, where do we stop this little process here? Never. Okay, so what we do is we put a plus and then we put an ellipses, a dot, 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 just to indicate that that pattern is going to continue. If you wanted to write it down like this, there's no problem doing that. Okay, you can go ahead and do that. Either way is fine. I kind of like this better. Okay, any questions there? Okay, so the next thing we're going to do is we're going to talk about something called a partial sum. So we're going to take this problem right here, and we're actually going to find the sum. We're going to add these up. This is a finite sum because we're going to start by plugging in a 1, in which case we get a 3. Then we're going to plug in a 2 and we get a 6. And then we're going to plug in a 3 and we get a 9, and we stop right there. So the partial sum is what we get for an actual answer if we add all these together. So the partial sum is 18. Okay, now this actually has a more specific name. This is called the third partial sum. Any ideas why it's the third partial sum? Because you added up the first 3 terms. So if this is the third partial sum, what's this one going to be called? Okay, this is going to be the fifth partial sum. So we get 3 plus 6 plus 9 plus 12 plus 15. If we add all those together, we get 45. Isn't that right? Double check me there. Okay, sometimes we'll call this S sub 3 for third partial sum, S for sum. Call this one S sub 5 for the fifth partial sum. What name would we give this? Okay, this is going to be the nth partial sum. We're going to call it S sub n, the sum of the first n terms. Okay? And the way we'd write this down, we'd have to write it down this way. This would be 3 plus 6 plus 9 plus dot, dot, dot. Now, this isn't an infinite sum, so we've got to put a last term on there. What would we put? Okay, what's the last number we plug in? N. So we plug it in right here. So the last one is we put a plus 3n. Now, we're actually going to learn how to add those up. In this particular case, it would be a formula. Okay? And hopefully we get to a point where we can figure out what that formula is. I'm actually going to give you part of that as kind of a homework assignment. Not that particular one, but something like it. Okay? So the next one says, express the following sums using sigma notation. So you'll notice this is kind of the opposite of what we were doing. Sigma notation here, you write it in expanded form. Write it in expanded form, actually find the sum, actually add them up. Here we've got the expanded form, and we want to write down sigma notation, that nice condensed packed form. So we're going to have a sigma, and there's my sigma. Okay, this one uses k, so I'm going to stick with that for the time being. I'm going to say k equals. Now, you do have a little bit of latitude to figure out what you want to start with, but again, normally we start with 1. But we've got to figure out what formula goes right here so that it produces the right series. So any idea on what the formula would be here? Just K. Now, before you just blindly take Brandon's word for it, let's double check and make sure that this works. If you plug in a 1, does that produce the first term? It does. If you plug in a 2, it produces the next one and so forth. Okay, so there's the right formula. How do we tell it where to stop? By the upper limit up here. And what are we going to put? We're going to put 40 there. Okay? So there is sigma notation that represents that series right there. Any questions? Slightly more difficult here. I'm going to write the sigma. I'm going to write k equals 1. This one's associated with a 1, that one's associated with a 2, that one's associated with a 3, then a 4, and so forth. Don't say anything out loud. Take your guess at what the formula should be. Any ideas? Logan? 2k. Let's check and make sure that it works. If you plug in a 1, does it produce the first term? Plug in a 2, does it produce the second term? And so forth. It does. Then the question is, where do we stop? Okay, do we go to 38? We don't. We go to the number that we'd plug in that would produce 38. So one way I can do this is I can say, when does 2k equal 38? Divide by 2, and I get 19. K equals 19 would produce the last one. So this would represent the 19th partial sum for that particular series. Any questions? Okay, would you do this one, please? And when you get done, check with your neighbor. Again, notice how nice it is that it's not simplified. This one, I would hope, would be about the easiest one that we've got on here. What's the numerator? K. Denominator? K plus 1. And where do we stop? It's written right there for us. It's right in the formula. Hardly have to do anything there. Okay. I do want to point this out. Everybody watch, please. This might seem a little bit silly on this problem, but in general, this is a good idea. Remember how we took the last term and set it equal to the formula? Watch this. When does 13 over, whoops, let me just write this. When does that equal k over k plus 1? So if you set k equal to the top and k plus 1 equal to the bottom, you'd still get k equals 13. That's the k that would produce the last term. Does that make sense? Handy little skill. Okay, let's take a look at the next couple, and we've only got that many more to take a look at. And some of these are relatively easy. It says find the partial sum here. So this is the fourth partial sum, so we're going to take the first 4 terms, all of which are 6s. So it's a constant. 24. Okay, 8th partial sum. Now I could go through and I could write down -5 plus -5 plus -5 all the way to the last one. But what's the easiest way to do this one if they're always constant? Okay, so on this one, -5 times 8 would be -40. On this one, 4 times 6 would be 24. Okay? So the easiest way to sum things up if they're always the same, if they're always a constant, is to do this. We'll just take the number of terms that we're adding up, start at 1 and go to n. That means there would be n of those terms, and times it by whatever the constant is. Does that make sense? So even if I did something weird like this, let's say I did I equals 1 to n of 1,000. How many 1,000s would I have? I'd have n of them, so I could do n times 1,000, and that would be the answer. So what I'm saying here is that, and this seems a little bit weird, what I'm saying here is the sum can be figured out if you just tell me what n is. So if you tell me n is 7, I'm going to put a 7 there. If you tell me it's 52, I'm going to put a 52 there. Got it? Okay. All right. So let's take a look at this problem right here. Now, we had a couple people in this class that have seen sequences and series before. So if you know how to do this problem, please don't say anything. This is the one that I'm going to give you as a little bit of a homework problem, okay? To see if you can figure this out. If you can't figure it out, I'll show you what it is tomorrow. And please don't look in your book, look ahead in your book or anything like that, okay? There was a young man that was probably somewhere between 8 and maybe 11 or 12 years old, lived 300-400 years ago, that figured this out. His teacher in little schoolhouse got upset with the class because they wouldn't keep their mouths shut and said, you know what, sit down and take your slate and add up the first 1,000 integers. Okay, first 1,000 counting numbers. So we could sit down and we could do something like this. And notice the index has changed here. Again, we're using i's now. Okay, start off with 1. That would be the first partial sum. 2, that would be the second partial sum. The second partial sum would be 3. Third partial sum would be 6 if you add those up. Then 10 and so forth. Okay, so you can kind of keep track of what the partial sums are, but he's going to go like this, all the way to 998, 999, and 1,000, and then he's going to stop. Yeah. You didn't catch that? You might think about it on your own. There are several different ways to do this problem, okay? But think about if you spot some patterns, like let's just say you go from 1 to 10. That answer is not too bad to find, okay? Maybe you go from 1 to 20. You could add those up. You could just have a calculator and add them up and see what you end up with. You might see some patterns. We're going to talk about how you can find this. And if you know how to find the answer, that's great. If you don't, we're going to figure it out tomorrow. Okay, any questions? Okay, last little bit. I want to take a look at some of the properties of series. I've got some examples here that have some similarities and some differences. So take a look at this one right here. Okay, notice that the index, the counter, has changed. Normally we use i's, j's, and k's, and sometimes m's and n's and stuff like that. So the counter is going to start at 1 and go to 5. So if I plug in a 1, I get a 2. Plug in a 2, I get a 4, a 6, an 8, and I know I stop at the 5th one, I stop at 10. Okay. If I add those up, let's see, there's a 10. Well, this adds up to 30, doesn't it? Okay, take a look at this one. What's the difference here? Okay, j equals 0 to 4, and we've got this formula. So if I plug in a 0, I get 2. If I plug in a 1, I get 4. If I plug in a 2, I get 6. If I plug in a 3, I get 8. And if I plug in a 4, I get 10. Exact same partial sum. Exact same series. So the difference is, remember we talked about this. Notice how this formula, most of the time, is going to be easier if we start off by plugging in a 1. But because on a summation notation, when we're using sigma, we can indicate what we want to start with and where we want to stop, we've got a few more options. And occasionally that's nice to do. In fact, you could represent this exact same thing a ton of different ways. Say we wanted to start at -7 and add up those 5 terms. We could just adjust the formula so that it produces the right terms. But again, generally the easiest way to go is start at 1. Second easiest is start at 0. Anything outside that is usually not very conventional. Not that it's not useful, it just doesn't come up as often. Okay, any questions there? Okay. So if you take a look at this one right here, I'm going to change colors again. Let's figure out what this one is. If I plug in a 0, I get 0. Then I get a 2. Then I get a 4. Then I get a 6. And then I get an 8. So if I add these up, I end up with 20. Then a big plus. So there's that first one. What's this one going to be? You have to be a little bit careful about this one. How many terms? Count with me. Start where? 0, 1, 2, 3, 4. 5 terms here, right? What are every one of those terms? A 2. So what's the partial sum? 5 times 2 is 10. Okay? So if I add this partial sum to that partial sum, then my answer on this one is 30. So this is the idea that you can take something a formula that's made of 2 separate terms, okay? And most of you are going to take calculus, so this is a big deal sooner or later. Everybody watch, please. You can take this sum that's made of 2 different pieces, okay? So this formula has a 2j plus a 2, okay? And I can break it into 2 separate summation notation, and I can figure that answer out right there. Okay, figure this one out, figure that one out, and then add them together, and I get the answer. Okay, that's one property of series. Okay, let's take a look at this next one. This starts at 1 and goes to 4, and these are all the perfect squares. So this is going to be a 1, a 4, a 9, and a 16. Okay, now, oddly enough, if I add those together, what do I get? I happen to get 30. Okay? Okay, this one is very similar, but just a little bit different. It's the same expression, it's just been multiplied by 3. So if you plug in a 1, you square that, you get a 1. Times it by 3, you get 3. Plug in a 2, you get a 4. Times it by 3, you get 12. Plug in a 3, times it by 3, you get 27. Plug in a 4, this is going to be 48. Okay, these two make 60. These two make 30. So what's the sum? 90. Do you see any relationship between the two of these? It's 3 times as big, right? Why is it 3 times as big? Because every term got multiplied by 3. So one thing that you can do, take a look at this right here, is you could change this so it's k equals 1 to 4, pull the 3 out front, and you've got your answer. Separate this piece. So if you know what the two of these are, and don't we know what this one is? Okay, so this would be 3 times 30 minus 30. So what's the answer to this one going to be? The answer to this one's going to be 60. And we can take advantage of the fact that we already knew what those answers are. All we did was multiply it by 3 and subtract what that sum was. Okay? Any questions? Okay. This is the last problem on these lecture notes. I think I actually copied this one right out of the textbook. You have a couple problems like this. Please spend the time to think about this because this is really, really important. Okay? This is going to be a big deal in the next couple of sections. So I'm going to blow this up, and it says, given this series right here, find the first, second, and third partial sums. So the first partial sum is what I get when I plug in a 1, and that's it. It's 3 over 10. So 3 over 10 to the first is just 10. Here's the second partial sum. If I plug in a 1, I get 3/10. If I plug in a 2, I get 3/100. So if I get a common denominator here of 100, what do I end up with? 33/100. Okay? Let's do the third partial sum. That's going to be 3/10 plus 3/100. What's the next one? Next term? 3/1000. Let's get a common denominator. So what's the partial sum? 333,000. Okay, what would you guess the fourth partial sum is? 333 over 10,000, right? And so forth. Okay, does anybody know what this adds up to? What is the sum if we just let this go on forever and ever and ever? Did an infinite sum never stop this process, just continued adding? Okay, watch. What's this as a decimal? 0.3. What's this? 0.33, right? What's this? 0.333, okay? The next partial sum would be 0.333. The fifth one would be 5 threes. So what if I wrote something down like this, and how do I indicate that this just goes on forever? Put a bar above it. What does that mean? It never ends. So what would it represent? Okay, it's an infinite number of threes. You've never seen this number before? What is it? It's 1/3. If you continued that process forever, so it took 3/10 plus 3/100 plus 3,000 plus 3/10,000 plus 300,000 and so forth. If you continued that forever, this addition problem going on forever would actually add up to the fraction 1/3. Okay? Now, you've got a problem on your assignment where this is a 6. And that's the only difference. Okay? There are a couple others there. Okay? We're actually going to get to the bottom of why this works the way it does. Let's see, not the next section, but the one after that. Okay? But you can kind of follow that as a model to do this one. Okay? So you can get through the assignment. Okay, are there any questions? Okay, did anybody try the homework?